KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
Neet, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, we started numericals. So two problems we discussed in the last class, right? So now we start from third problem, right? See here. So in the third problem, right, when the electromagnetic radiations of frequencies 4 into 10 to the power of 15 Hz and 6 into 10 to the power of 15 Hz fall on the same metal, okay, in different experiments, right? In different experiments, okay. The ratio of maximum kinetic energy of electrons liberated. The ratio of maximum kinetic energy of electrons liberated is 1:3. 1:3. Full stop. The threshold frequency for the metal is. Okay. So what I am saying is, in this problem, they have given electromagnetic radiations of frequencies. So they have given frequencies of electromagnetic radiations, right? In one case it is 4 into 10 to the power of 15 Hz. In the next case it is 6 into 10 to the power of 15 Hz, right? Fall on the same metal, okay. After completion of this, here in different experiments, the ratio of maximum kinetic energy of electrons, is, that is 1:3, full stop. The threshold frequency for the metal is, right, that we have to find. See here. Now we are going to see the answer or solution, okay, right. See here. According to Einstein's photoelectric equation, E is equal to phi naught plus Ke maximum. So the same thing you can write it as H nu is equal to H nu naught plus Ke maximum. Okay, right. So for first experiment, because the metal is same in both the experiments, anyhow for first experiment, H into 4 into 10 to the power of 15 is equal to H nu naught plus X. It is what equation number 1, right? Next, here the ratio of maximum kinetic energy of the electrons liberated is 1:3, right? So when it is 1:3, suppose in one case it is X means, in another case it is 3X, right? In first experiment it is X means, in the second experiment it is 3X. If you want to find the ratio, X by 3X, that is what 1:3, okay. Finally he is asking the threshold frequency for the metal is, okay, right. And in for second experiment the same procedure, H into 6 into 10 to the power of 15 is equal to H nu naught plus 3X, okay, right. So this is like equation number 1. it is like equation number 2, right? So from equations 1 and 2, so by solving these two equations, because here this will get cancelled, no? So by solving these two equations, right, you can find out the value of x. By solving these two, first you can find out the value of x. By writing the value of x in any one of the equation, right, you can find out the value of nu naught, that is what? Threshold frequency for the metal. Threshold frequency for the metal, okay? Threshold frequency for the metal, okay? See here, so we get nu naught is equal to, that is what he is asking to find, threshold frequency, right? So solving of two equations is your wish, right? So you can equate, see, just by subtracting this one from this one, these two will get cancelled, then you can find out the x value, right? After finding the x value, by writing in any one of the equations, you can find out the, that is what, threshold frequency for the metal, right? It is not the thing, but what I am saying is, otherwise directly also you can do, because that is what, see here, you just multiply this with 3x will come here, and then you subtract, these two will get cancelled, because here also 3x will come, and then 3x will get cancelled. Directly you can go for nu naught, right? That is your wish, right? That's, I am not saying. And finally, you just see here, that is what, we got nu naught as 3 into 10 to the power of 15. 3 into 10 to the power of 15 Hz. 3 into 10 to the power of 15 Hz, that is what, threshold frequency, right? Students, did you understand what is meant by threshold frequency? What is meant by threshold frequency? Did you understand? Because while explaining the synopsis, I told you many times what is threshold frequency, right? The minimum frequency of incident radiation, threshold frequency is the minimum frequency of incident radiations required to eject the electron from metal surface. The minimum frequency of radiation required to eject the electron from a metallic surface is called threshold frequency, right? In these two experiments, the metal is same. We didn't change the metal. And we got the threshold frequency as 3 into 10 to the power of 15 Hz. Okay, right. Next question, the fourth question. If K1 and K2, if K1 and K2 are maximum kinetic energies of photoelectrons emitted when lights of wavelengths, lambda 1 and lambda 2 respectively, lambda 1 and lambda 2 respectively, respectively incident on a metallic surface. If K1 and K2 are maximum kinetic energies of photoelectrons emitted when lights of wavelengths lambda 1 and lambda 2 respectively incident on a metallic surface, right? Incident on a metallic surface, right? Okay. If lambda 1 is equal to 3 lambda 2, if lambda 1 is equal to 3 lambda 2, then what is the solution? What about the relation between K1 and K2? That we have to find. Okay. Observe carefully. While solving this problem, you have to keep in mind what is photoelectric effect, right? So when a metallic surface is exposed, to the electromagnetic radiation, that is invisible form of energy, right? Then emission of electrons takes place from that metallic surface. Okay. So this phenomena is called as photoelectric effect. Okay, right. So if K1 and K2 are maximum kinetic energies of photoelectrons emitted when lights of wavelength lambda 1 and lambda 2 respectively incident on a metallic surface. If lambda 1 is equal to 3 lambda, it is the relation between the wavelengths of light incident on a metallic surface, asking to find the relation between kinetic energies of photoelectrons. Kinetic energies of photoelectrons, right? So whenever I am explaining the problem, from this chapter, you have to keep in mind what's happening in case of photoelectric effect. What is happening in case of photoelectric effect? Then by the completion of the solution, you will get a complete picture, complete clarity. So what they are asking and what we found, etc. Okay, right. See here, solution. See this now. So this you can write it as no. This is what E is equal to W naught plus K. Right. So two things are here, two cases or two situations. Okay. Hc by lambda 1 is equal to, in first case, Hc by lambda 1, because 2 are there, no, definitely have to mention 1 and 2. For constants, no need, because Planck's constant here and speed of light here, Planck's constant here and speed of light there, right? So in case of these two, need not write H1C1 and H2C2, because constant is same throughout the universe, right? Okay. So in first case, Hc by lambda 1 is equal to W naught plus K1. W naught plus K1, right? Hc by lambda 2 is equal to W naught plus K2. Hc by lambda 2 is equal to W naught plus K2. Okay, right. And it is like equation 1 and it is like equation 2, right? From equations 1 and 2, Hc into 1 by Hc by lambda 2 minus Hc by lambda 1. Hc into 1 by lambda 2 minus 1 by lambda 1 is equal to, W naught plus K2 minus W naught plus K1. So that what is, these two will get cancelled. W naught, that is what work function will get cancelled for two cases. So when we combine these two equations. So finally what we are getting, K2 minus K1. K2 minus K1, okay, right. And Hc into 1 by lambda 2 minus, in place of lambda 1, he is asking to take 3 lambda 2. 3 lambda 2. So Hc into 1 by lambda 2 minus 1 by 3 lambda 2 is equal to K2 minus K1. K2 minus K1, that is equation number 3. Equation number 3, right. So from these two equations, we are getting one more equations and including the substitution. Okay, right. Whether you can assume as 3 or you can also assume this one as 3, right. So finally, if you take lambda 2 also outside, Hc by lambda 2. So see here, so we are getting third equation by solving from 1 and 2, right. So from third equation you can write like this, Hc by lambda 2 into 2 by 3 is equal to K2 minus K1. So Hc by lambda 2 is equal to 3 by 2 into K2 minus K1. 3 by 2 into K2 minus K1. So finally you can write it as the relation between K1 and K2. That is what maximum kinetic energies of photoelectrons, right. So K1 is less than K2 by 3. K1 is less than K2 by 3. So that you can say K1 is less than K2 by 3. Okay, right. Next, next question we are going for fifth question, right. See here, what retarding potential is necessary? What retarding potential is necessary to stop the emission of photoelectrons? To stop the emission of photoelectrons if the work function of the target material is 1.24 electron volt and wavelength of incident light is 436, right. 436, that is here in case of in this case of problem, it is what 436 nanometer, right. 436 nanometer, and the value of nano, that is what 10 to the power of minus 9. Okay, nano is 10 to the power of minus 9. Okay, right. You just focus on the problem of first, what retarding potential potential is necessary to stop the emission of photoelectrons. To stop the emission of photoelectrons, right? If the work function of the target material is 1.24 electron volt. You know, when we talked about stopping potential, I explained you clearly. You just assume P like emitter plate and Q like collecting plate or collecting material. You know, at a particular instant of time, for a particular value of that is collector plate, you know, no electron will reach the collector plate, so that you can say that the photocurrent is 0. That is the situation we need here. That is the situation we need here. You know, he is asking what retarding potential is necessary to stop the emission of photoelectrons. To stop the emission of photoelectrons. Okay, right. And you know, further they have given work function of the target material, that is 1.24 electron volt, and wavelength of incident light as 436 nanometers. 436 nanometers, right? So, and asking to take Hc as 1240 electron volt meter. Electron volt meter. Just sorry for saying ma, it is what electron volt nanometer, right? Electron volt nanometer, right? So that is what Hc by, so it is Hc is equal to 1240 electron volt nanometer here. And after that here it's a part of question, right? Now we are going for solution, right? You please keep in mind what is the question they have given and what is the information he is asking to expect. Okay, that is very important for us, because the complete solution to solve as much as simple, right? So Neet point of view, for one question we have to take only 1 minute time, right? So to complete the solution in 1 minute, we have to understand the question clearly and completely and correctly within short interval of time, right? Then you can go for solution. See here, energy of photon E is equal to h nu, that is equal to Hc by lambda, or E is equal to, because Hc is 1240, no? So 1240 electron volt nanometer, you know, divided by lambda is 436. Lambda is 436 nanometers, right? And this value of 436 also given, no? Value of 436 also given. That is what wavelength of incident light, right? So by taking this Hc and lambda, I can find out that energy of the photon as 2.84 electron volt. 2.84 electron volt. You know that here nanometer will get cancelled. Then finally the answer will be 2.84 electron volt. Okay, which is the unit of energy, right? Next, according to Einstein's equation for photoelectric effect, that is K maximum is equal to h nu. K maximum is equal to h nu minus phi naught. That is what photoelectric equation, right? And there itself, by substituting the values of h nu and phi naught, you know, we can get the value of K maximum. That is how much here? K maximum is equal to 2.84 minus 1.24, right? So if you do that process, that is mathematical process, then you will get it as, right? So 2.84 minus 1.24 means it is 1.6 EV, that is electron volt. Okay, so after completion of that, because after completion of calculating maximum kinetic energy from Einstein's photoelectric equation, that is Ke maximum or K maximum is equal to h nu minus phi naught, that is as 1.6 electron volts. Now we are going to calculate, that is what stopping potential, right? We know this relation, right? So in our previous class I explained you the important formulae along with the total number of formulas present in this chapter, dual nature of light. So K maximum is equal to E into Vs, right? Sometimes we are using V naught to represent that is what stopping potential, and sometimes we are using Vs. Vs is also stopping potential, right? And similarly, in case of work function also, sometimes we are using W naught, right? But sometimes we are using phi naught, right? So don't confuse that. Either phi naught or W naught, both are for representation, both to represent work function only. Vs and V naught both are using to represent stopping potential only. Okay. So K maximum is equal to E into Vs. That is what here 1.6 electron volt. 1.6 electron volt is equal to E into Vs. So E will get cancelled. Finally, Vs is equal to 1.6 volt. Stopping potential is 1.6 volt. Okay, that is what he is asking to calculate, and we calculated. Next problem, see here. A metallic surface is irradiated by monochromatic light of frequency nu1 and stopping potential is found to be V1. Full stop. If the light of frequency nu2 irradiates the surface, the stopping potential will be right. So like two different situations, different situations means nearly same. The thing is same, the major concept is same, but two different situations or two different cases, right? So when a metallic surface is irradiated by a monochromatic light of frequency nu1 and stopping potential is found to be V1. If the light of frequency nu2 irradiates the surface, the stopping potential will be right. That he is asking. Okay. So maximum kinetic energy K maximum is equal to half mv square. That it is not nu, it is V. Half mv square. That is equal to E into Vs. That's even from here also we got it. So here E is that what like charge of electron, and Vs is the stopping potential, right? So here he mentioned that Vs is the stopping potential. After that, same as that is what we are considering. We are taking Einstein's photoelectric equation. That is what, according to Einstein's photoelectric effect, H nu1 is equal to phi naught plus E V1. And H nu2 is equal to phi naught plus E V2. So you please keep in mind the work function is same. Right? So H nu1 is equal to phi naught plus E V1 and H nu2 is equal to phi naught plus E V2. So it is like equation 1 and equation 2 when we applied photoelectric equation for these two situations according to the problem. Okay. Now we are trying to get H into nu1 minus nu2. That is what very well 1 minus 2. Equation 2 we are subtracting from equation 1. So therefore H into nu1 minus nu2 is equal to E into V1 minus V2. So finally taking E to this side, H by E into nu1 minus nu2 is equal to V1 minus V2. H by E into nu1 minus nu2 is equal to V1 minus V2. Finally, V2 is equal to V1 plus H by E. V1 plus H by E into nu1 minus nu2. Right? So he is asking the stopping potential in second case. That is actually V2 only. Right? So V2 is equal to V1 plus H by E into nu1 minus nu2, right? So that is what he is asking. So how we got Einstein's photoelectric equation, that is what H nu is equal to phi naught plus EV, we applied to two different situations according to the problem, right? So according to the problem, for situation 1, H nu1 is equal to phi naught plus EV1. And for second situation, H nu2 is equal to phi naught plus E V2. That is what equation number 2, right? So therefore, H into nu1 minus nu2 is equal to E into V1 minus V2. E into V1 minus V2. Okay. Finally, H by E into nu1 minus nu2 is equal to V1 minus V2. So mathematically, at last you can write V2 is equal to V1 plus H by E into nu1 minus nu2. Nu1 minus nu2. Okay. Right. So next problem, that is 7th problem. See here. Capital A and capital B are two metals with threshold frequencies 1.8 into 10 to the power of 14 Hz and 2.2 into 10 to the power of 14 Hz. Full stop. Photons of energy 0.825 electron volt are incident on them. Then photoelectrons are emitted in. So there are two things, A and B. So in which photoelectrons are emitted? Either A or B or both or none of them, either A or B. I mean no A and not A and not B, right? So that is he is asking to get. Right. You know the formula for phi naught, that is what H, see here. See phi naught, right? So it is H into nu naught by E, H into nu naught by E, electron volt, right? So when it is correct, you know, just this is the formula, is a formula for work function that he is writing in terms of electron volt. Okay, and when he is writing electron volt, we have to write like this. Okay, and H nu naught by E into electron volt and H nu naught and E. Okay, and if you do this process, you will get it as 0.74 electron volt. 0.74 electron volt. Similarly for B, 0.91 into electron volt. Okay, same process, but the metal is different now. So here it is 1.8 into 10 to the power of 14, that is what threshold frequency, and here it is 2.2 into 10 to the power of 10 to the power of 14, 10 to the power of 14, that is what threshold frequency, right? So when it is 10 to the power of when it is 2.2 into 10 to the power of 14, finally we are getting the threshold, finally we are getting a stopping potential, finally we are getting work function. This is not the stopping potential, it is the work function. So we are getting work function as 0.91, 2.2 into 10 to the power of 14 is divided by this value. So as it is, how we did this one, similarly we did this one, right? So here we are getting 0.91 electron volt. You know, you understood what is photoelectric effect, right? Here it is 0.74 electron volt, it is 0.91 electron volts. In the question they have given this much of energy is incident on them, right? So if you compare this value, and these two values, you know, this is less than this and this is greater than this. So where that emission of electrons, right, where the situation possible according to the question, that is what then photoelectrons are emitted in, right? See here, since the incident energy 0.825 electron volt is greater than 0.74 electron volt and less than 0.91 electron volt, right? Therefore photoelectrons are emitted from metal A only. Okay, right. So in this class we discussed 5 problems, that is from 3, 4, 5 and 6, 7 also. Okay, right. So remaining problem we will continue in the next class. Thank you.